This is the second explanation video of physical quantities and measurement. In the last class, we learned how to determine the density of regular and irregular solids. Today, we will learn how to determine densities of liquids. As density is the ratio of mass and volume, to determine density of liquid, we must find mass and volume of given quantity of liquid. See activity 4. Here we are trying to calculate density of a liquid. Suppose milk is given here. So first we have to take a empty beaker and measure its mass. Suppose m1 gram. Now with a measuring can we will measure 100 ml of milk. Then we will transfer the measured milk into the beaker and again determine the mass. Let it be m2. Next mass of the milk will be m2 minus m1. That means the filled jar minus the empty one, and the volume of the milk is 100 ml or 100 cc. So by the formula of density D equal to m by v, if we calculate this one, we can have the density of milk calculated. Suppose here m1 is 40 gram and m2 is 143 gram after filling it up with 100 ml of milk. Now the volume of milk is 100 ml or 100 semi-cube. So mass of the milk m equal to m2 minus m1, which is 103 gram. Now the density of milk D equal to m by v is formula 103 by 100, 1.03 gram per semi-cube. Next, we will learn how to measure density using a density bottle. Figure 2.1, page number 35. A density bottle. Follow the activity 5. So first a dry empty density bottle have to be taken and its weight is taken in beam balance. After that, the liquid which density will be measured will be filled in it to the brim. Then mass of the filled bottle would be taken. If we subtract both, we will get the mass of the liquid for taken volume of it. Now using the formula D equal to m by v, we can have its density. Activity 5. So suppose the empty bottle's mass m1 is 27 gram and the filled bottle mass m2, that is 92 gram. Now mass of the liquid is m2 minus m1, that is 65 gram. Bottle's capacity 50 ml or 50 semi-cube. So the density 65 by 50, 1.3 gram per semi-cube. Similar numericals are given in page number 35 and 36. Practice those carefully. Next, we are moving to relative density. This term may be new. Let me explain this. So relative density is needed to compare between object on their heaviness or lightness. So relative density is the ratio of density of substance to density of pure water at 4 degrees Celsius. So RD equal to density of substance by density of water at 4 degrees Celsius if we present this mathematically. Follow along page number 36. So in case of relative density, water's density at 4 degrees Celsius will be compared with the liquid's density that you are trying to measure, or any other thing's density that you are trying to measure. Now relative density is a ratio. That's why it is unitless. And why here only water have been mentioned? Because density of water is 1000 kg per meter cube or 1 gram per semi-cube only at 4 degrees Celsius. It is easier to calculate with water's density, and also that have to be taken in 4 degrees Celsius. Also, relative density of a substance may be defined as the ratio of the mass of given volume of any substance to the mass of equal volume of water at 4 degrees Celsius. Next, in page number 37, some substances relative density is given. Memorize some of these. Table 2.2, relative density for iron, mercury, ice, glycerin and kerosene. As it is told just before, relative density is unitless because it is ratio of two densities. See here, one example is given that copper 8900 kg per meter cube and water density at 4 degrees Celsius is 1000 kg per meter cube. So the relative density for copper is 8.9. So just because it is a ratio, that's why it is unitless. Now another thing, the relation between relative density and normal density. Okay, so relative density is equal to density of a substance by density of water at 4 degrees Celsius. That is the formula. And the relation of density and relative density is density equal to relative density into 1000 kg per meter cube. Okay, from that formula we can calculate this, because water density is 1000 kg per meter cube. Also, density is equal to relative density numerically, but relative density has no unit. And relative density of a substance is numerically equal to its density expressed in gram per semicube. Next, the effect of temperature on density. Okay, the mass of an object never changes, but volume of an object changes due to temperature. Generally, volume increase in heating and reduces in cooling. Follow along page number 38. So, if volume increases in heating and reduces in cooling, then density of the object decrease with increase in temperature, because volume increases here, and density of an object increases with decrease in temperature because volume decrease here. So when temperature increases, density will decrease, and when temperature decreases, density will increase. Volume of liquid and gas both increase with increase in temperature, and density of a liquid changes with temperature, so relative density also changes. Now try to do the checkpoint 2 in the book. Also, checkpoint 1's answer key will be given at the last of this video. The next part of the chapter is about floating and sinking. Okay, so if an object is placed over a liquid whose density is less than the density of the object, then the object sinks. On the other hand, if density of liquid is more than the object, then it will float. See here at activity 6. Iron block sinks in water, wooden block partially floats, and cork block floats almost on water surface. The blocks are of same size, so density is different in the cases. Iron is here the most dense, so it sinks, and cork block is the least dense, that's why it floats completely on top of the water. Next is principle of flotation. According to the principle of flotation, a solid will sink in a liquid if its density is more than the density of the liquid, but a solid will float on liquid if its density is less than the density of a liquid. Follow page number 39, applications of flotation. Here a picture of an iceberg is given. How larger icebergs stay afloat on top of the water. The density of ice is less than the density of water. Hence, huge masses of ice called iceberg continue to float on water. Also, metal ships. Okay, page number 40, figure number 2.4. A large ship's picture is given there that also floats on top of water. Okay, so iron ship is designed in such a way that it is mostly hollow from within. The bottom part is also mostly hollow, thus the volume of the iron ship becomes very large as compared to the mass of it. Hence the effective density becomes less because air is inside it. Okay, so now it can float on water. Fishes have air bladder inside their body, so when they suck up a lot of the air, the density becomes very less, their body's density becomes very less, so now they can stay afloat, and when they release that air, their body's density increases and so they sinks in the water. Another thing, that a helium balloon floats in the air. A helium gas is less dense than normal air, so that's why that helium filled balloon rises up and floats. At page number 41, checkpoint 3, try to do this in the book as well. Okay, this concludes this chapter, and here is the answer key for checkpoint 1 at page number 34. Thank you.